was mentored by Dr. Bopp this semester.
Hi, my name is Lilly Habart.
Hi, I'm McKenzie.
Hi, I'm Hayden Pendergrass.
I'm Mason Seegars.
I'm Grace Ann Johnson.
And I'm Jackson Phillips. I want everyone to think of the number 3 in their head. Now add 2, take away 1, add 3. I won't grade your answers, but if you ever get the number 7, that is your working memory in action. Working memory is a limited capacity system that allows us to temporarily store and manipulate information. In simple terms, it's basically storing and using information at the same time. These are the 2 most common models of working memory. Working memory is used in an array of things like reasoning, learning, and knowing what you're doing in real time. And then how does working memory, another example of working memory is remembering directions while driving a car, or remembering the steps of a math problem while completing it. So how does this relate to our study? The in-back task is a common test used to measure working memory. The in-back task asks one to identify a stimulus or an image and remember if it matches in trials back. N is basically just a variable that represents how many trials back you are trying to identify a match. As you can see on the screen, each number represents the space in between an item you are currently looking at and one you are trying to see if they match. To help visualize this, each stimulus or each box represents what a participant would actively be seeing while taking the test. First, they'd start with a stimulus, and they see a blank screen, another stimulus, blank, and so forth. And they continue this process while looking for a match until they find one. In our particular test, we did the 2 back. So this would represent a match, or a hit, which is what our participants are trying to identify. And they continue this process, so on. So because the in-back task places because the in-back task places a continuous demand on working memory, it allows us to see the difference between age groups.
Now, there are many different ways to measure working memory. In this prior study, a forward and backward span task were used, assessing the number of items that younger and older adults were able to recall. Shown in red are younger adults from the ages of 16 to 19 who were able to recall more items as compared to older adults who ranged from the age of 70 to 79. This indicates an age-related working memory deficit. As Jackson mentioned, the in-back is a task that is commonly used to measure working memory. In this study, a 1-back and 2-back tasks were completed by older and younger adults. As can be seen by the figure, older adults, shown in the lighter gray color, had a reduced accuracy compared to younger adults across both the 1- and 2-back tasks. Additionally, both age groups decreased in accuracy as the task increased in difficulty from a 1-back to a 2-back. Next, previous research has indicated that within the working memory system, there are separate stimuli and they are processed differently within working memory. In this model specifically, we can see the visual processing and the verbal processing areas highlighted in blue. This study specifically looked at the number of items participants were able to recall in a verbal and visual task. In red, we can see that the visual task had decreased number of items that participants can recall. An additional study looked at abilities of younger adults, shown in black, and older adults, shown here by the horizontal lines, in verbal and visual tasks. Shown by the green line is that older adults had an increased or a decreased working memory performance for the visual task. Lastly, we are also looked at a previous study, and this is a prior working memory model that shows that long-term memory impacts working memory capability. Specifically, having access to semantic knowledge increases and enhances ties to all aspects of working memory. A prior study looked at verbal semantic knowledge via a vocabulary test for older and younger adults. Shown here is that older adults in blue had higher vocab test scores when compared to younger adults.
In this study, we're examining whether age-related differences in working memory can be reduced by how information is encoded, and how long it stays active in the brain. By memory trace, it refers to the brain briefly keeping information active for a few seconds. We already know that working memory decreases with age, So we're looking at whether the differences are present and whether they vary depending on the task, specifically verbal versus visual conditions. We are also interested in the role of semantic knowledge and such as familiarity or meaning. For example, concrete images are more easily pictured and connected to, so they can be more easily remembered compared to the abstract figures and stimuli. The idea is that when information is more meaningful, it is encoded stronger, which helps maintain that memory trace longer. In turn, this may help reduce some of the age-related differences we typically see in working memory performance. To assess working memory, we used a two-back task in which participants had to decide whether the current item matched the item given 2 trials earlier. We measured both accuracy and response time to evaluate performance of all conditions.
Well, younger adults and older adults completed 8 different conditions of the NBAC, with four verbal conditions consisting of concrete words, abstract words, slur words, trigrams, four visual conditions consisting of concrete line drawings, semi-nameable line drawings, non-nameable line drawings, and abstract shapes. A normative study was conducted on undergraduates in which semi-nameable and non-nameable were done, in which semi-nameable had more familiarity and identifiability versus non-nameable line drawings. In this, we can see that the semi-nameable line drawing has a heart-shaped item, and this non-nameable line drawing has more of an abstract shape. In this, there is a linear progression of more knowledge to the least amount of knowledge utilized, in which concrete words and concrete line drawings are more nameable and identifiable, while trigrams, a group of 3 consonants and abstract shapes, have a least amount of nameability. In this, each NBAC task for each of the 8 conditions had 54 total items, and 36 of which were non-targets and 18 were targets. In total, it took participants around 20 minutes to complete the task, and of this, a strategy questionnaire was given to assess how the NBAC was conducted on participants. In this approach worked memory conditions across verbal and visual conditions. Now we have our examples. In this, we have our concrete words. As we can see, the red indicates not a match, while the green indicates a match. And in this, we have beach and elbow, which are not a match. However, deer and deer are a match. And now we have our visual condition, which is a concrete line drawing. And of this, we have hippo and crab not being a match, and rose being a match.
So now we'll get into our results. So first I'm going to break down what the graphs will look like, and then we'll get into the results. So we looked at accuracy on the NBAC in terms of D prime, which is a sensitivity measure that takes into account guessing. And as Hayden mentioned, we looked at verbal stimuli and visual stimuli that ranged from high to low in knowledge. And then we compared performance between young adults seen in black and older adults seen in gold. And so rather than showing you all the data, I'm going to break it down into specific comparisons that we made. First, we looked at verbal versus visual stimuli in the high knowledge condition. So we looked at concrete words for verbal and concrete line drawings for visual. So our results showed that for our verbal stimuli, there was no age difference in NBAC performance, indicating no working memory difference. And for our visual stimuli, we found that older adults did perform worse than younger adults on the NBAC. And so from this, we see that in the high knowledge condition, there's only a difference in NBAC performance for the visual stimuli. So next we'll look at our no knowledge condition, comparing verbal and visual. So verbal is our non-words, which we combined pseudo-words and trigrams. And then our visual is abstract line drawings, which we combined semi-nameable line drawings and non-nameable line drawings. And so our results show once again that for our verbal stimuli, there was no difference in NBAC performance. And for our visual stimuli, the older adults did perform worse than the younger adults. And so from this we see that with no knowledge, there's only a difference in visual stimuli. So overall, when we look at our comparison, we find that for verbal stimuli and for visual stimuli, knowledge increases performance for both of these for both age groups. There was no difference in knowledge between age groups. But we do find that regardless of knowledge present in a stimuli, the age difference is only present in the visual stimuli, indicating that working memory performance is different for visual, but then we find that for verbal stimuli, there is no age deficit when processing verbal information.
So I'm going to go over these next results really quickly, and then any questions, I'll answer them at the end. But as Hayden mentioned, we asked participants what their strategy was when they completed the MBAC. And they're categorized into groups that you can see up here. So for the verbal tasks, both older and younger adults seem to commonly use a repetition repetition strategy, which is shown in this dark green. However, in the visual stimuli, we saw a much more diffuse number of strategies, and more participants reported using no conscious strategy, which is shown in this lime green. And so based on the total of our results, we were able to conclude that first, knowledge benefits both younger and older adults, which supports our hypothesis. We likely see this because when you already have a memory of something, when you're shown that item again, you already have familiarity, which elicits a stronger brain signal or trace. And so that makes it easier to encode into your working memory, which then improves working memory performance. We also saw that there was no age difference with verbal stimuli between older and younger adults in their working memory performance. However, when those stimuli were images, we saw that older adults performed worse. And this was unexpected, but we think that we see this because we only showed our stimuli for a very short period of time. General slowing occurs as we age, and it reduces the speed but not the quality of cognition. And so younger adults are able to see an image and turn that into words in their head, whereas older adults are not able to do that because of the time constraint, which is why we think we see the impaired performance. And so, what does this look like in the real world? As Jackson mentioned, mental math is an example of a working memory task that we use every day. And so we would not realistically or hypothetically see that there would be any differences in older and younger adults in completing a task such as calculating a tip at a restaurant.
We'd like to thank everyone who participated in our study and engaged in our research. Between the 6 of us, it took approximately 90 hours to test everyone. And we are just so extremely grateful for Dr. Bopp and the Wofford community for everything that they did.